Hello folks, we have reached the end of chapter 8 with our last section about modeling motion with parametric equations. So the purpose of parametric equations is to get to the point where we can use the vertical and horizontal components of a projectile to find parametric equations that represent the path of that projectile. So I'm just going to show you this graph here. You don't need to draw this, but just kind of look at it with me for a second. Basically, a projectile is anything, that is thrown or kicked or launched from either the ground or someone holding it. And paths of objects, due to gravity, will have a quadratic sort of shape. And an upside down one, though, obviously with a negative sign up front. So, it goes up and then at some point it levels out here and then it comes back down. All of these vectors across my projectile motion represent given velocities in the horizontal and vertical parts at any given point in time. Okay, so this is the x-axis here would be considered time. The y-axis would be considered distance. So distance and time. So this talks about the different velocities at any given moment for that projectile motion. Okay, so let's just do a couple of examples that are very, very basic using this idea. So I want you to find oops, that's not a font size. There we go. Okay. Find the initial horizontal and vertical velocities of the given situations. Again, you don't have to write every single word, but it is important that you write enough or abbreviate enough to know what type of question it is, because the questions on your assignment and on the review and on the test are going to be worded very similarly. Okay, so I want you to find the initial horizontal and vertical velocities of the scenario of a soccer ball that is kicked with an initial velocity of 33 feet per second at an angle of 29 degrees with the ground. An angle of 29, let me put a degree symbol here, with the ground. So you could have actually have done this question even before this video. Essentially, if you create, even though the path of the projectile is going to make this quadratic parabola shape, at that one moment in time, that initial horizontal and vertical velocities can be drawn as a right triangle, as I'm being concerned with these horizontal and vertical vectors of that initial spot. So basically, that initial velocity of 33 feet per second is going to act as the magnitude of that of the motion of it being kicked. In this case, the hypotenuse of the triangle. And then if I label my triangle, I've got the 29 degree angle with the ground. When I want to know the horizontal and vertical velocities of the situation. So the horizontal situation would be denoted like this. The magnitude of the vector v sub x. So basically, this is the notation for the horizontal velocity, which we've also used that absolute value for magnitude. And the same thing for the vertical velocity. It's just going to be the absolute value of vector v sub y. So we know horizontal goes along the x-axis. So that one's always going to be horizontal, and then the vertical one will always go along with the y-axis. So all I'm asking you to do is solve for these. So if we use SOHCAHTOA, I can set up a couple of equations to solve for these. So first I can say, let me find the horizontal first, since that's what I've always written. I can use a cosine of 29. It's going to equal adjacent over hypotenuse. So adjacent will be the horizontal velocity over the hypotenuse is 33, that initial velocity. And then to solve for that horizontal velocity, I get that the horizontal velocity is going to be, if I multiply both sides by 33 times the cosine of 29. Again, you need to check that your calculator is in degree mode. The default is radian, so always check and make sure that you're in degree mode before you type this in. You should end up with the horizontal velocity. For the sake of this whole video, and unless otherwise specified, let's round to the nearest hundredth. It's going to be about 28.86. We are in, our units here are going to be feet per second. So that is our initial horizontal velocity. And we can do the same thing to find the vertical. We can say this time, though, that the sine of 29 degrees is equal to the initial vertical velocity, v sub y, over 33. Same thing, we're going to cross multiply or multiply both sides by 33. So then we get that our initial vertical velocity will be 33 times the sine of 29. And you get your answer is going to be, this should be approximately 16 feet per second. So those are the initial, if you put v sub x, I understand that that is horizontal. Same thing, v sub y. That's an understood notation of vertical. So you don't have to put the words horizontal and vertical. Okay, let's do one more like this. I want you to find the initial horizontal and vertical velocities of a situation in which a golf ball is struck with an initial velocity. Sometimes, by the way, you may see that as v sub 0 for initial velocity. So if that ever pops up, oh, did it convert my, I don't know what it's doing here. Okay, I'll write that in a second. V sub 0 of 16 feet per second at an angle of 38 degrees with the ground. So again, I want you to find the initial horizontal and vertical. So initial velocity might be written as v sub 0, 38 degrees. So you're going to do the same thing, and the quote-unquote formula is the same every time, so you might get pretty quick with not having to draw a picture and knowing the numbers that are going to go where. But if I draw a picture of that scenario, this initial velocity is going to be 16. The horizontal component will look like this. The vertical velocity has this notation. The angle is 38 degrees with the ground. So again, if I set up, okay, well, the cosine of 38 degrees is adjacent over hypotenuse. So it's going to be the horizontal velocity over the hypotenuse is 16, meaning we can solve for that horizontal velocity by doing 16 times the cosine of 38. Which rounded to the nearest hundredth will be approximately 12.61 feet per second. So there's the initial horizontal velocity. We can do the same thing with vertical. We just need to change our trig function to sine. So the sine of 38 degrees will be the vertical velocity over 16. Multiply both sides by 16 times the sine of 38. We get our vertical velocity, v sub y, which will be approximately 9.85 feet per second. Now, as far as showing work goes, you don't necessarily have to have the picture, although having the picture is almost adequate in and of itself. And I don't need to see both of these steps, I would need to at least see one or the other. Which one of these, are you using? Maybe the one, whatever one you're typing in your calculator could be the one that you write down. So it's not necessary that you do everything, but I at least need to see a little bit of it. Okay, so that's the basics. Now, parametric equations for projectile paths as a whole. So maybe, well, parametric equations for projectile paths. So not just with any kind of motion, but particularly with these projectiles that are going to have that parabolic shape. Now, since horizontal velocity in any scenario is unaffected by gravity, it is the magnitude of the horizontal component of the initial velocity. Okay, so this implies that in words, I have that the horizontal velocity is equal to, the horizontal distance is what I'm trying to say, is equal to the horizontal velocity times time. And you've seen this before, distance is equal to rate times time. That's exactly what this is, except specifically dealing with the horizontal distance. So if I convert these words into mathematical variables, horizontal distance is going to be denoted by x. And then horizontal velocity, we've already discussed as going to be this notation. It's going to be basically what we did up here. It's going to be that magnitude of vector v times the cosine of theta times time. We're going to use the variable t. So this is how you find the horizontal distance of a projectile path. Okay. Now, vertical velocity is affected by gravity, so we must adjust the vertical components. By subtracting the vertical displacement due to gravity from the vertical displacement caused by the initial velocity, then we can determine the height of the projectile after however many number of seconds, again using t for that. So the height in feet or meters, sometimes you're going to see, of a free-falling object affected by gravity is given by the equation. So I'm going to write these out here to the side. Height is equal to 1/2 gt squared, and that may ring a bell, where g for gravity has two potential units. Either gravity is going to be in meters per second, which is 9.8 meters per second squared, or depending on the units of your problem, gravity will be 32 feet per second squared. So over here, vertical displacement is going to equal the displacement due to initial velocity, minus displacement due to gravity. Okay, and here we're using, horizontal distance versus vertical displacement. Because it's a projectile path of that, it's going to be a parabola. Sometimes your vertical displacement is how much it's displaced from that horizontal line down at the bottom, and you're going to hit that point twice, right? So, if you throw a baseball up into the air and we talk about its vertical location, it's going to have two different instances, perhaps, where it's 5 feet above the ground. So that's one of the main differences as well, which is why you also have a squared term. Converting this into units, we're going to have y is equal to displacement due to initial velocity is going to be written as our vertical velocity times time, so just like the horizontal distance, but we have to subtract the displacement due to gravity, which is where the 1/2 gt squared comes from. So if I clean these up a little bit, because typically when you plug in a number for time, it's going to, that variable kind of shifts to the front. In general, what you need to know is your parametric equations for projectile paths are going to be denoted as x equals t times the horizontal velocity, and then y is going to equal t times the vertical velocity, so that one involves the sine of theta, minus the displacement due to gravity, so minus 1/2 gt squared. So these two equations are the big takeaways. These are your parametric equations for projectile paths. So if you did not write this, that's what this stands for in this cloud, parametric equations for projectile paths. So we're going to do one example that's going to have about 3 different parts that shows you how to use these types of equations. Okay, so let's do, I think if I'm numbering, this will be example 3. Okay, let's say a rock is tossed into a lake with an initial velocity of 15 meters per second at an angle of 8 degrees with the ground. A rock is tossed into a lake with an initial velocity of 15 meters per second at an angle of 8 degrees with the ground. So this one's going to be a 3-part question. Part A is going to be to use these equations. So it's going to say write a parametric equation, or write, actually it's going to be 2, right? 1 for x and 1 for y. So write parametric equations to describe the path of the rock. Right, parametric equations to describe the path of the rock. So let's look at what we know. We know the initial velocity is 15 meters per second. So that is going to be, anytime we see this notation, the magnitude of that vector, that's going to be what our initial velocity is. And then obviously 8 degrees is going to be our angle. So for the x parametric equation, x is going to equal, I'll write the equation without substituting anything, t times the initial velocity in the horizontal direction. So that's going to be, x is going to equal, we are substituting in 15 for that initial velocity, so t times 15 times the cosine of, I should have put theta over here instead of the angle, times the cosine of 8 degrees. And then again, just to clear this up a little bit, typically we're going to write, why did I put 15? I would like for you to change this to 5 meters per second. That was a typo. Okay, so this is going to be t times 5 times cosine of 8 degrees. So again, typically we would switch these variables. So we'd put 5t times the cosine of 8 degrees. That is the horizontal parametric equation. The vertical parametric equation is given by t times that initial velocity minus 1/2 gt squared. So again, I'm substituting in 5 for initial velocity. So y will equal t, we don't know what time is, that's remaining a variable, times 5 times the sine of 8 degrees minus 1/2. As far as g goes, we are dealing with meters per second. So that's how we know that we're going to be using 9.8 for gravity, 9.8 meters per second squared. If our units were given in feet, we would use the number 32 for g. Okay, but we're going to be using 9.8. So 1/2 times 9.8 times t squared. So then if I simplify this a bit, I'd get y is equal to 5t times the sine of 8 degrees minus, I can go ahead and simplify these to 1/2 times 9.8 is going to be 4.9 t squared. So then that is the parametric equation for the vertical part. Okay, once you have those parametric equations, we can answer some questions. So part B is going to say, after 3 seconds, how far has the rock traveled both horizontally and vertically? And that's where these equations are going to come into play. So now I have a value for time after 3 seconds. So this time I'm substituting in 3 everywhere I see t, and I'm going to simplify. And since I'm asking for both horizontally and vertically, you're going to plug it into each of the parametric equations. Okay, so let's do horizontally first. We're going to get x equals 5 instead of t, I'm plugging in times 3 times the cosine of 8 degrees. And this time you're actually going to plug this into your calculator and simplify. Again, verifying that you are in degree mode. So essentially 15 times the cosine of 8 degrees. To the nearest hundredth, you should get about 14.85. Again, we always need to include our units. So how far has it traveled horizontally? About 14.85 meters. Substitute in the same value into the y equation. Y equals 5 times, instead of t, time is 3 seconds, so 5 times 3, times the sine of 8 degrees, minus 4.9 times 3 squared. 4.9 times 3 squared. And you could break this all up, or you could do this all at once, or you could break it up into a couple of different ones. I think I did not complete mine, and I think this is going to be a negative number, and this is dangerous because I totally forgot this aspect of subtracting off our gravity factor. Oh, would you look at that? I've got a negative number for my vertical velocity. That is fan-stinking-tastic. Okay. Typically, I'm not stopping this video because I'm too far in. Typically, when you plug in these numbers, and this is what I get for picking my own numbers for an equation instead of just grabbing one out the book or something. When you plug in your initial velocity somewhere in the y direction, you will get a positive number. So this one, let's just omit this part. And you can blame it on Miss Chouinier's terrible values that she chose. Here, this is saying the force of gravity is apparently way too much, and maybe our rock would fall into the ground because it was so hard. I don't know. Either that, or honestly, what probably is happening is at a time of 3 seconds, the rock has probably already hit the ground. So this initial velocity of 5 meters per second is not enough to sustain the rock beyond 3 seconds. So if that time were something smaller than 3, that's where it might actually work a little bit better. Okay, so if that causes confusion as you do the assignment that goes along with this, let me know. But typically it's going to work when you have better values. Okay, the last question is going to be, how long will it take the rock to travel 20 meters from its starting point? How long will it take the rock to travel 20 meters from its starting point? The thing you have to realize here is that even though it does not use the word, this is talking about a horizontal distance, right, from its starting point. We can assume that it is talking about its horizontal distance. That being said, if we use, let's go back to our regular horizontal equation, x is equal to 5t times the cosine of 8 degrees. what's happening here is instead of giving you a time, I'm giving you a distance. So I'm going to substitute in 20 for x, and then I want to solve for time. So 20 is equal to 5t times the cosine of 8 degrees. And then if I want to isolate t, then remember that cosine of 8 degrees is a number, and so is 5. So I can take care of both of those in one fell swoop. If I divide this by 5 times the cosine of 8, then it will cancel with both of those. And then I will divide the left side also by 5 times the cosine of 8, which means t will equal 20 divided by 5 times the cosine of 8. Round it to the nearest hundredth. Time is going to be approximately 4.04 seconds. Okay, sorry about that mix-up. If anything else seems kind of weird, you know the drill. Let me know about it so I can make sure to address it in class.